Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be finishing Chapter 3.5 and look at how to identify vector subspaces. In these four questions, or four examples, I would like to determine if the given subset W is a subspace of the given vector space V. And if it is not, I'd like to be able to say why it's not. Or if it is, I'd like to be able to say why it is. So let's look at the first one. Consider the vector space R2. So you're probably thinking, let's start by drawing a coordinate system. So here's your vector space R2. And we're asking, is this a subspace? Now what I'd like you to recognize is that W, the equation of a W, is all the ordered pairs x and y that satisfy x squared plus y squared is 4, which you'd like to recognize as the equation of a circle whose radius is 2. And so since the radius is 2, we should know that some of the points that live on the circle, at least some easy ones, might be 2, 0, negative 2, 0, 0, 2, maybe 0, negative 2. And so we either want to verify that this is a vector space by showing the closure properties, or identify which of the properties it fails. So let's look at the first one, addition. We should be able to find two solutions and show that the sum of these two solutions is still a solution. So maybe some easy ones to grab might be like the solutions 2, 0 and 0, 2. These both live in W. So 2, 0 plus 0, 2. This would be 2, 2. Is 2, 2 a solution? Notice that 2, 2 would be approximately here. And 2, 2 is not a solution. It's not part of W. So this would be not an element of W. And since it's not an element of W, we have failed the closure of addition, which tells us W cannot be a subspace. We're technically done. However, just for practice, I would like to look at some of the others with you. How about scalar multiplication? If you did any constant times a solution, notice that this is also failed since 6, 0 would not be a solution either. We could have also checked for the presence of a 0 vector. So here we're talking about the ordered pair 0, 0. Is 0, 0 an element of W? And notice that 0, 0 would technically be the origin. And notice that the origin is not a solution to our equation and not an element of W. Either way, it would not matter which of the three properties I displayed here. We should be able to say W is not a subspace of R2. But again, you could have used any one of those to show that it was not a subspace. I just wanted to do all three for practice. Let's try another one. Consider the vector space R3. Is this definition of W a subspace? Oops, my pen slipped. Let me try that again. So R3 is a three-dimensional space. People typically show this by only representing the positive X, Y, and Z axis. So we're talking about R3, all of 3 space, but then we maintain that Y has to be 0. Notice that if Y is 0, we would be stuck in the XZ plane. If Y is 0, then X and Z is what's allowed to have values in it. So we'd be looking at maybe vectors that move off in this direction in the XZ plane, or vectors that move in that direction in the XZ plane. So we want to know, is this definition of W enough to call this a subspace? So let's check our closure requirements. Let's first look at addition. If we were to add two elements of W together, maybe one element of W might look like X1, 0, Z1. A second element of W might look like X2, 0, Z2. Notice I'm maintaining that Y has to be 0. If we add these two vectors together, oh, not Y1. Then what we get back is a vector still of 3 components, but the Y component would still be 0. This would be an element of W. I think that's enough to say that we have closure of addition. Let's go on to the second property. Do we have closure of scalar multiplication? So imagine now we have some positive scalar k, or positive or any scalar k, times an element of W. A scalar multiple would still be a vector with 3 components where the middle is 0. This would still be an element of W. Is there a 0 vector? Here the 0 vector would look like 0, 0, 0. And that's an element of W. I think this is enough for us to conclude that yes, W is a subspace of R3. Okay, let's try another one. Consider the vector space P3. And notice I wrote that P3 wrong. It should actually be written with a lowercase with a subscript, not a superscript. So this should actually say your vector space is P3 like this. So W is polynomials where the degree equals 3. Now there's a small thing to pay attention here. When we talk about P3, P3 is polynomials of degree 3 or less. So technically P3 looks like things of the form a t cubed plus b t squared plus c t plus d, such that a, b, c, and d are elements of the real numbers. However, W are only those elements where the degree is always 3. So we're still saying if we require the degree always be 3, not less than or equal to 3, will this still be a vector space? So let's consider vector addition for a moment. And let's imagine adding two polynomials together. Maybe a first polynomial could be 2x cubed plus 3x plus 1. This is an element of W. It's a polynomial where the degree is 3. And let's add this to another polynomial. What if we added it to negative 2x cubed plus 3x squared plus x? If we were to add these two polynomials by combining like terms, I think we could say the 2x cubed would cancel with the negative 2x cubed. And what we would get back would be 3x squared plus 3x plus 2. Notice that this is no longer a degree 3 polynomial. And since it's not a degree 3 polynomial, we could also probably say this is not a element of W anymore. So we just showed that we could take two elements of W and add them together and they're no longer in W. This tells us that W is not a subspace of P3. And it's because we require that the degree always be equal to 3 is what made that happen. Okay, let's try one last one. Consider the vector space C2, 0, 1. And you may have to look back in our notes to recall what this vector space was. And what you want to remember is C201 is functions with continuous second derivatives on the interval 0 to 1. So it's saying consider all functions with continuous second derivatives on the interval 0 to 1. And there are so many you can't write them down. There are hundreds and hundreds of continuous functions that have continuous second derivatives. So let's just represent these. Let's let f1 and f2 be elements of W. Meaning they satisfy this. It means f1 double prime plus f1 has to equal 0. That's what it means to be an element of W, is that only consider those functions that satisfy this requirement. And it also means that f2 double prime plus f2 has to equal 0. That's what it means for f1 and f2 to be elements of W. What we want to be able to show is that these functions satisfy the closure properties. So let's look at first the sum. If you looked at f1 plus f2 double prime plus f1 plus f2, will this still equal 0? Meaning, will the sum replace f with f1, f2? Will the sum still be an element of W? Recalling what we know from calculus, that the second derivative of the sum is really the sum of the second derivatives. And we could choose to rewrite these functions to get similar terms together. So maybe we could write this as f1 double prime plus f1 and group f2 double prime with f2. Notice that since f1 was an element of W, this had to be 0. And f2 was an element of W, so this had to be 0. So notice that this is equal to 0, and this verifies that we have closure of vector addition. Okay. Let's also check our second closure property, scalar multiplication. So here we want to show that some constant times of element in W is still an element of W. So I'm taking some function f1 that's in W, because we said it was, and we're looking at a constant multiple of it and seeing if it still satisfies our same equation. So again, from calculus, we want to recall that whenever you have the derivative of a constant times a function, that is the same as a constant times the derivative of the function. Notice we can factor out the common factor of k. And since f1 was an element of w, to start with, we know this has to be 0. So we have k times 0, which is equal to 0. And this verifies of scalar multiplication. And since we have satisfied the closure properties, we can now state W is a subspace of functions that have continuous second derivatives on the interval 0 to 1. Check. Okay, I hope this is helpful. I think this should give you all the examples that you need for completing your homework in Chapter 3.5, and I will see you next time.